Let's take a look at some of the questions from our test review for the second half of Unit 1. In this first question, we have a deposit of $8,000 being made into an account with an annual interest rate of 6% compounded monthly. If no further deposits are made, how much time will it take for the investment to quadruple? So this is an exponential growth question, and let's just remember our formula here. The amount of money in our account is going to be equal to the principal times 1 plus r divided by n raised to the nt power, where n is the number of times it's compounded, r is the rate, t is time, and p is the principal or the original amount of our money. So we can substitute values into this formula. Our principal or our initial amount of money is $8,000. 1 plus our rate. Now the rate is 6%, but I need to change that to a decimal. So 0.06 divided by the number of times it's going to be compounded, which in this case is going to be 12 times a year because it's compounded monthly. And so we're going to raise that to the 12t power. And the question is asking us, how long does it take our investment to quadruple? So I want to know how long it takes for my $8,000 to turn into $32,000, because 8,000 times 4 is 32,000. So now we have an exponential equation that we need to solve. So our first step here is going to be to divide by 8,000. Whoops, sorry about that. If I divide both sides by 8,000, I'm going to get 1 plus 0.06 over 12 to the 12t is equal to 4. 32,000 divided by 8 would be 4. Now I have an exponential equation, and I need to undo the exponential. And so I'm going to use a log, and we're going to use, even though it's kind of strange, this is going to be the base of our log, because that's the base of my exponential. So if I log both sides, log base 1 plus 0.06 over 12 of 1 plus 0.06 over 12 to the 12t power is equal to log base 1 plus 0.06 over 12 of 4. So over here on the left side, the log undoes the exponential. Basically, these two things cancel out, and I'm left with 12t is equal to log with this very strange base. But that's okay, it's still a number of 4. And then our final step, let me see where I have room to write this. Our last thing to do here would be to divide by 12. And so I think I'm going to go right over here. So t is going to be equal to the log with our strange base, 1 plus 0.06 over 12 of 4, all divided by 12. And this would be an exact answer. So this question on your test is actually going to be on the no calculator section. And your answer choices will look something like this, because this is what we could enter into the calculator to get an actual answer. Let's look at our next question. Oh, I hit the wrong button. Here we go. Next question. Sketch the graph of these following functions. So these questions are, seeing if we understand what an exponential graph looks like. And as I do this, I'm going to kind of make some connections in a couple different ways. I'm going to connect it back to geometric sequences. I'm also going to make some connections to transformations of functions. So on this first one, y is equal to 4 times 0.25 to the x. So looking at that equation, one of the first things that I want you to identify is your y-intercept. Now in this case, well, in any case, the y-intercept is going to be whatever value you get when x is 0. And so if x is 0, 0.25 to the 0 would be 1 times 4 is 4. And hopefully you remember seeing that in class, that we've seen with these exponential functions that whatever value is here in the front, the initial value, that's going to be your y-intercept. So now the question is, what does our graph look like? Now what's interesting about this one is that our base is a decimal that's less than 1. It's 0.25. And so let's just think about this, maybe a table of values. We just figured out that if x is 0, y is equal to 4. Well, what if x is 1? What if my x value is 1? Then I get 4 times 0.25 to the 1, which is equal to, whoops, I wrote 24, didn't I? 4 times 0.25 to the 1, which is 4 times 0.25, which is just 1. And so the next point on my graph would be, say, right here at 1, 1. Just based on those 2 points alone, and the fact that I know this is an exponential function, we can see that the function would look something like this. Now you might be wondering why it's decreasing, because we don't have a negative x value. That's often what makes our function, our exponential function, decrease. But this time what makes it decrease is that the base here is a value less than 1. And if you remember with geometric sequences, whenever our radius was less, I'm sorry, not our radius, our ratio was less than 1, then the values in the sequence, they got smaller as we went along. So we end up with a decreasing exponential function. All right, question B. Let me erase some of this to get it out of the way, but I'll replace that. We got 1. On question B, this time my starting value is negative 0.25. So I know on my graph that my y-intercept is going to be down here somewhere. And this time my base is 4, and my x is negative. Now let's think about what happens here. First of all, let's just imagine that we have 0.25 times 4 to the x. Let's just for right now, I'm not going to think about those negative signs, but just if we had it like this. For this function, we know that our y-intercept would be 0.25. Then we're multiplying by 4. Our ratio is 4, which means the next number should be 4 times as great as the one that I'm at. So that would be like at 1, 1. It's going to be bigger. And so based on those 2 points, we're going to get a graph that looks like this. Now let's consider those negative numbers. The negative signs. First of all, this negative that's on the x, since the negative is on the x, that's going to reflect my graph over the y-axis. And so I have the same graph, but reflected like this. Now let's consider this negative in front of the whole thing. If my whole function is negative, then that takes the graph and flips it or reflects it over the x-axis. And so my final graph here is this blue one. And this one is actually our answer. Last one, question C. 0.25 times 4 to the negative x. So notice this is very similar to question B, except that we don't have that negative in front. And so we've actually already figured out this graph. But let's just talk about it one more time. 0.25 times 4, let's just pretend that it was just to the x. Well, then I know that my y-intercept is 0.25. And if the base of my exponential is 4, that means the next term should be 4 times greater. So it's going to be bigger, it's going to go up. And so that function would look like this. But when I introduce the negative, when I make that x negative, then it's going to reflect this function over the y-axis, and I end up with this. And this pink graph here, that would be our final graph for part C. Question number 3, describe the end behavior as x goes to infinity of the following types of functions. So again, another question about these exponential growth, exponential decay type graphs. For exponential growth, an exponential growth graph would look like this. And we're wanting to describe the end behavior as x goes to positive infinity, which of course is out here. And so for this graph, as x is going to infinity, where is my y value going? Well, y is also going to infinity. Now on the exponential decay graph, that graph should be decreasing. If our value or the number is decaying or it's decreasing, our graph ends up decreasing. And so now, as x goes to infinity, if we look at our y values here, they're actually approaching 0.